Hello everyone, and this episode of Drawing Lewis Structures is brought to you by selenium dioxide, which has the formula SeO2. And we're going to draw the Lewis structure for this one again using the 5 steps from our Drawing Lewis Structures document. So step 1 is to sum the valence electrons for all the atoms that you have available, and so we go to the periodic table and we find out, take a moment to go check out selenium and ask yourself how many valence electrons selenium will have. It happens to be in the same column as oxygen, so they will end up with the same number of valence electrons. Hopefully you checked your periodic table and found out that selenium is in column 6, and oxygen is also in column 6, but there's 2 of them, so I'm going to double that one. So I have a total of 18 electrons that I am needing to represent in my molecule. Great, that's step 1. Step 2 says, draw the skeleton structure. So the selenium is going to go in the middle, and we will add the oxygens to each side. Now, you have some freedom here. You could draw them up and down or up to the side. It really doesn't matter, as long as the oxygens are connected to the selenium in whatever way you see fit. So, we've used up 2 and 4 electrons. We have to represent 18, so we keep going with step 3. Step 3 says, start with the outermost atoms, give each one of them an octet of electrons. So we're going to give each oxygen 6 more, so that each oxygen ends up with a total of 8. So now I've used 2, 4, 6, 8, 10, 12, 14, 16 electrons. And I have 18 total, so I need 2 more. Step 4 says that if you have leftover electrons, they go on the central atom in a pair. Okay, so we've accomplished step 4. We've used up all 18 electrons. Now, up to this point, we have not made use of step number 5. And in this case, we are going to have to make use of step number 5, because after step 4, you should scan over your molecule to make sure that all the atoms have an octet. Now, this oxygen has an octet, this oxygen has an octet, but this selenium does not have an octet. It has 2, 4, 6, but not 8. And I can't just go in and pencil in 2 more dots because I've just used up all my dots. So what do we do? Step 5 says, if, and you're not going to use this all the time, but if you don't have enough electrons to give the central atom an octet, try a multiple bond. Alright, and what does this mean? What it means is that the selenium, because it's already sharing electrons with the oxygen, and these oxygens have those extra electrons available for them, they can actually share a second or even a third pair of electrons when necessary. So what happens is you would take a pair of electrons off of one of the oxygens. Just go ahead and scratch it out. We don't need to be completely neat and everything about this. And we're going to move them in toward the middle and make a second bonding pair of electrons. So now these don't exist anymore. But now the oxygen's got 2 lone pairs, but also is sharing 2 of its pairs of electrons with the selenium. And the selenium now has 2, 4, 6, 8 electrons. So you use double and triple bonds when the central atom needs more electrons, but you've run out using your total. Okay. Now, if you're following along at home, you might be sitting there wondering, well, why didn't you do it on this side? Well, the answer to that question, very good question by the way, is that I could have done it on that side. You can choose whichever side you would like to make that double bond. In fact, I'm going to go ahead and redraw this. Just very quickly. To show that this is just as equally valid as this. So if you draw your double bond on this side, or somebody else draws it on this side, you've essentially drawn the same thing in mirror image form, and they're both valid, they're both correct, and in fact both of them probably exist at any given time because electrons are mobile, and this double bond might shift over to this side and back and forth and back and forth in a process called resonance. So we will get to resonance again more in detail at some point, but both of those are both correct, and more likely it's more correct to say that they both exist one at any given time, and they oscillate between each other. Okay, and there's your first double bonded molecule.